Hi, this is an example problem on the kinematics of uniform circular motion. This is a realistic problem here, or true life problem here, about an astronaut that spent time up in the International Space Station. So take a moment, pause, and read the question here. All right, so for this type of problem, a kinematics problem, uniform circular motion, there's essentially four different variables that we can use, and they're related in two equations. So if you look at these equations for uniform circular motion, we've got one for the speed v equals 2 pi r over t, and a separate one for the centripetal acceleration. And if we consider these two equations, notice that there's four different variables between. We have r, t, v, and ac. And we go ahead and draw a little picture of what this might look like. So at the center we have Earth, and around the Earth we've got the International Space Station going in a circle. And we might say at the instant it's right here. What does the velocity vector look like? Tangent to the curve. And of course, the magnitude of that vector, that's your v right here, the speed. You've got the radius as well. So if we look at the distance from the very center of the circular orbit out to where the satellite is located, r is your radius, that's this guy over here. We've also got the centripetal acceleration, which is always pointing straight in towards the middle of the circle. So there's your AC there. And finally, T. T is the time that it takes to make one complete revolution all the way around, right? So in a time T, you go all the way around one time. So let's look at our equations again. We can see that V equals 2 pi r over T is one of those. And of course, that's just how fast you're going. Distance of one full trip around divided by time of one full trip around, right? So that makes sense. And the other one is simply a formula that tells us that the centripetal acceleration is given by the speed squared divided by the radius. And so we can work with those two. So let's go ahead and write down these three variables and see which of these we know and what things we are trying to solve for. We're given some information here. We have a constant speed of 7,667 meters per second. So we know what v is. We can go ahead and write that down right here. We're asked to calculate Christina's orbital radius, so we want to know what r is, and the centripetal acceleration. Now, if you can get any two of these, then you can get all the rest, right? So somehow we must be able to figure out what t is so we can calculate for the other ones. If we look at it carefully, it says that Christina spent 328 days orbiting Earth, and she completed 4,850 circular orbit. So let's see if we can solve for t, the time it takes to make one complete circular orbit. So if we think about it, right, we've got a time here in days, 328 days, and that's 4,850 circular orbits. Well, if we divide that by 4,850 orbits, we'll get the time in days that it takes to make just one circular orbit. And so if we go ahead and put that in the calculator, we end up with this number, 0.0676 days. And that's one orbit, right? That's pretty amazing. So yeah, you can see how fast you're going around the Earth and the International Space Station, right? It's a very small fraction of a day to actually go all the way around one time the entire Earth. Of course, that's because you're going at a high speed. Now, to convert this into a time unit that we need to be consistent here, well, we've got seconds here, right? So we need to convert this into seconds. Let's do a unit conversion. 0.0676 days. What do we have? we're going to say 1 day, 24 hours, right? And each hour, 3,600 seconds, and we can go ahead and calculate this time in seconds. Cancel out our units here, end up in seconds, and this turn comes out to be 5,843 seconds to be able to complete that orbit. Now, now that we know what t is, we can go ahead and write this down. If you divide that number by 60, that comes out to about 97 minutes. It's about an hour and a half to go all the way around the Earth in the ISS. All right, let's see if we can focus on solving some of the other things now. At this point, we can choose which of these equations are going to work based on the information that we have. The first question is figure out what is the radius. Find the radius of the orbit of the ISS. All right, well, let's see. We know what t and v are. It looks like this equation will allow us to solve for r, so let's go ahead and do that. I'm going to go ahead and write that equation down, and I'll just rearrange both sides, or flip the sides, because I know I want to solve for r, and I like r to be on the left there. So at this point, we're just going to do a little bit of algebra. Let's go ahead and multiply both sides by t over 2 pi. In order to isolate the r, so we cancel out the 2 pi, cancel out the t, and we find out that r is equal to vt over 2 pi, and we plug in our. And so inserting our numbers, canceling our units out, we end up with 7.13 times 10 to the 6th meters. Or in other words, a little bit more than 7 million meters is the radial distance of the orbit for the International Space Station. Let's calculate the centripetal acceleration. We're going to use the other equation here, and that's going to be the speed squared divided by the radius, now that we know the radius. So v in this case, 7,667 meters per second squared divided by the radius, 7.13 times 10 to the 6th meters. And we see that we'll end up with meters per second squared, and that answer comes out to about 8.24 meters per second squared. And there it is. And it's no coincidence that that's a little bit smaller than the gravitational acceleration g, because it is gravity that is causing the satellite to accelerate towards the center of the Earth, but the space shuttle is a little bit further out, and so it's a smaller value when you're further out from the surface there.